And today we're going to go through the basics of graph theory and then our specific research that we did in graph theory with anti-magic labeling. So kind of to get us started, so you guys have like a solid foundation of graph theory. So the definition of graph theory is the study of graphs. One second, let me move this. The study of graphs, which are mathematical structures used to model pairwise relations between objects. Specifically, a graph G consists of two sets, a non-empty finite set V of vertices and a set E of edges consisting of unordered pairs of distinct vertices from V. So if you look at that middle graph, you could see all the vertices are labeled A through F. So the vertices represents the dots on the graph, and then the lines in between the vertices are the edges. So you can see that middle graph is like pretty simple, and then if you look at the outside graphs, it gets pretty complicated sometimes. So in graph theory, there's kind of like a wide variety of graphs that you're going to deal with and see. And so graph theory can actually be applied to a lot of things outside of math. Some of these places include natural sciences, engineering, genetics, social sciences like psychology and sociology, and computer science. So if you look at that first graph to the right, you could see that is from electrical engineering, and you can see the relations between all the vertices and the edges and like all the components, so you could better understand electrical engineering. And then the one next to it is a graph for biology, and that's just showing the different surface levels of the water and the connections between all the lines and the vertices. So graph theory really helps us understand these different areas and helps us problem solve. So to create this foundation so you guys can understand our research, we let's go through some vocab really quickly. So a degree is a number of edges incident with the vertex. So if you look at that graph to the right, if you looked at vertex A, you can see there's three edges coming from it, which means that vertex A has a degree of 3. If you looked at vertex B, it would have a degree of 2 with the 2 edges coming from it, etc. So the chromatic index is the minimum number of colors necessary to properly color the edges of the graph. So we want to be able to label all the edges of the graph, but you can't label the same edges that are touching the same vertex with the same label. So in this case, we're going to use colors. So just to visually see it, you can see that we labeled that one red, and then you can't label the next one that's touching it red, so we labeled it blue, and then so on. And then that last edge that we want to label has to be a different color because the red and blue are both touching that vertex, so it'd be green. And then this graph would have a chromatic index of 3. So going on, connected graph means for any two vertices, A and B, there's a path from A to B. So if we were to go from E to vertex B, then we would start at E and then follow the edge to A and then follow the edge to B. So that means that this is a connected graph, and we could do that with any edge to, or any vertex to any vertex. A cubic graph means that all vertices have a degree of 3. So this is not a cubic graph, but if you look at vertex A, you can see that has a degree of 3. So if all the vertices were like that vertex, then this would be a cubic graph, but not all of them are like that, so it's not. A cycle is a path whose endpoints are the same vertex. So if you look at that graph and you start at A and you kind of go on like a cycle around, so you go from A to B to C to D and then back to A, and that would be a cycle. And then a subgraph is just a part of the main graph. So if we were to just take a piece of this graph and put it to the side, then that would be a subgraph. Now, to get a little info on our research. So we chose a family of graphs and determined a strategic strategy that produces an anti-magic labeling for each graph in the family of graphs. So we each took a family of graphs and picked one strategy that could work for any graph in that family of graphs. So there are many families of graphs that have already been determined to have anti-magic labelings, but we chose families of graphs that have not yet been examined. So I decided to research the flower star graph, and Victoria decided to research the single square chain graph. So now to get into my research a little bit. So you see, so I examined the flower star graph, and you can see those graphs at the top of the page. So to define it, a flower star graph is J sub n. It's a connected graph, meaning that you you go from any vertex to any other vertex just following the edges. It's bridgeless, meaning that if you were to take out one of the bridges, one of the edges, then it would still remain connected and there wouldn't be like a lone vertex in any place. It's a cubic graph, meaning that each vertex has a degree of 3 and it has a chromatic index of 4. So going back to the vocab, if we were to label the edges with the colors, it would have an chromatic index of 4. It has 6 n edges and 4 n vertices, and for n an odd integer greater than or equal to 3. So the flower stalk is always going to be labeled an odd number. It can never be labeled like J4. It can't be an even number because we figured out that if it was J4 or J6 or any of those even numbers, then when we labeled it with the colors, the chromatic index would actually be 3 instead of 4, so it would no longer be defined as a flower star graph. So now it's on the construction of the graph. So the n in the J sub n corresponds to the number of star graphs on 4 vertices. So first you want to construct the star graphs, then you want to label the vertices, A through D, and then you want to construct the inner cycle by connecting all the B's, and then construct the outer cycle by connecting all the C's, and then connecting all the D's. So I'll get into that right now. So this example of construction of the J3 graph, so you can see on the left, since it's 3, we're making 3 star graphs on 4 vertices. And then the next part, we're going to label each vertex A through D. And then the top right, we'll label them A1, A2, A3, and so on. So B1 through B3, and C1 through C3, and then D1 through D3. And that's just kind of like visually to make it easier to see how I connected everything. So you're going to start by connecting all the B's, so B1, B2, B3, with that inner cycle in the top left. And then we're going to connect the C's, so C1, C2 to C3. And then we're going to connect all the D's. So we're going to do that by connecting C3 to D1. And then we're going to connect all the D's, so D1 to D2 to D3. And then we're going to finish it off by connecting D3 to C1 with a horizontal line. And so after conducting my research, I was actually not able to find a specific strategy that could be applied to the whole family of graphs. So I was able to find a strategy that could be applied to like a specific one. So I would find a strategy for J3, and then that would be anti-magic. Then I would apply that to J5, and then J5 wouldn't be anti-magic, so I'd have to start all over again. So this is actually an example of a J3 strategy that I came up with that could only be applied to the J3 graph and no other graph. So just to break it down to the right, I started by labeling the edges in a cycle with that outside cycle kind of 1 through 6. And then I labeled the star graph 7, 8, 9 in clockwise direction. And then I labeled the inner cycle 16, 17, 18 in the clockwise direction. And then you could see here, these are all the vertex sums of the graph, and there's no similar vertex sums between all of them. So this would be anti-magic. So in conclusion with the flower snark, so although it's not able to determine a strategic anti-magic labeling technique that could be applied to all the J sub n graphs, I'm continuing to investigate this solution. And it's definitely more than likely that there is a generic strategy, but this is something that is yet to be determined.